Dear students, in this section we are going to discuss how to calculate potential energy of a dipole placed in an electric field. Suppose a dipole is placed in certain electric field. You can observe this dipole having the dipole moment P is placed in the electric field which is non-uniform, and it is placed at this position where electric field vector is E, right? We know the potential energy of a dipole placed in electric field is given by the expression U equal to minus P dot E. Okay. So, in coming illustration, we will learn how to apply this concept in different situations. So, let us move to situation number 1. In this illustration, you can observe electric dipole having dipole moment P is placed near a point charge, right? You can observe this point charge is placed at the equatorial position of the dipole at a distance small l. And here we need to find the potential energy of the system. In this system we have the two elements, one is dipole and second is the charged particle. Here we need to calculate the potential energy of the system. Okay, so let us make the diagram to the next page. This is the situation, and we know the potential energy of the system is given by U equal to minus P dot E. This is the expression. P is the dipole moment and E is the electric field, that is the external electric field, and external electric field is created because of this charged particle at the center of the dipole, and we know the electric field because of this point charge will be in the leftward direction like this. This is the electric field vector, right? That means the angle between the electric field vector and dipole moment vector is 90 degree. Now we can write this dot product as P is the dipole moment, E is the electric field, and electric field magnitude because of this point charge will be equal to 1 upon 4 pi epsilon naught Q divided by L square, and angle between these two is 90 degree. So we will write minus P multiplied by 4 pi epsilon naught Q divided by L square cos 90, and cos 90 we know it is equal to 0. That's why the potential energy of the system is equal to 0. Okay. Now let us move to second illustration. In this illustration, it is given for electrostatic charge system, charge and dipole system. You can observe here we need to calculate the potential energy of the system. Here the situation is slightly different. Here the charged particle is placed at the axial position of the dipole, and dipole moment is P, and distance of the point charge from the center of dipole is small l. Okay, this is the situation. And here also we can write the potential energy of the system as U equal to minus P dot E. This is the potential energy of the dipole and charged particle system. Okay, now we can make the electric field vector at the center of dipole because of this charged particle, and we know this is in the leftward direction like this. That means the angle between the dipole moment and electric field vector is 180 degree, and the magnitude of electric field is 1 upon 4 pi epsilon naught Q divided by L square. So this dot product can be written as P multiplied by 1 upon 4 pi epsilon naught Q divided by L square cos 180 degree, and negative sign of course like this. Okay, and cos 180 degree we know that is equal to minus 1. That means minus will be positive, and this value will be equal to 1 upon 4 pi epsilon naught PQ divided by L square. Okay, let us move to next illustration. Illustration number 3. Here you can observe we have two charged particles and one dipole. Dipole is placed at the middle of the charged particle, and both charged particles are separated at a distance L and L from the dipole. Okay, you can observe here the dipole is placed at the origin along the y-axis, and here we need to calculate the potential energy of the system. This is the situation. So let us make the diagram to the next page, this one. Okay, and let us write this object, this charged particle as 1, and number this charged particle as 2, and this is 3. We have 3 objects in our system. We are considering these 3 elements two charged particle and one dipole as a system, and we can observe here we are having three pairs, that is this charged particle and dipole pair, this dipole and charged particle pair, and this charged particle and this charged particle pair. That means we can write potential energy of the system as U12 plus U23 plus U13. This is U12 for these two charged particles, U23 for dipole and charged particle, and U13 for dipole and charged particle again. Here we can write U32 or U23, both are applicable. Here again we can understand, we can write U13 or U31. Okay, this can be written as U12 or U21. Both result will be the same. First of all, we can write direct expression for potential energy of this charged particle, which give U12. So let us write the potential energy of the charge number 1 and 2. This is equal to 1 upon 4 pi epsilon naught Q multiplied by Q, that is Q square divided by a separation, that is 2L. Okay. So this is the potential energies associated with the charge number 1 and 2. And here we can observe this charged particle and dipole and this charged particle and dipole are making identical type of configuration. That means the potential energy of 1,3 and 2,3 should be equal. So here we can write U13 equal to U23. Now let us calculate U13. So here we can write U13 is equal to minus P dot E1. P is the dipole moment of this dipole and E1 is the electric field because of charged particle number 1 at the center of the dipole. Okay, and we know the electric field because of this charged particle is positive. Then electric field because of this charged particle at the center of dipole will be in the rightward direction like this. So this is the E1 vector. Now you can observe the angle between the dipole moment and this electric field vector is 90 degree. That means this dot product will be equal to 0. That means the potential energy of the system, because this value 2, 3 and 1, 3 will be 0. That means the potential of the system U equal to U12, and U12 we have calculated this one. So we can write the potential energy of the system U equal to 1 upon 4 pi epsilon naught Q square divided by 2L. Now let us move to next illustration. In this illustration we can observe we are having the three charged particles of equal magnitude and same sign, and these three charged particles are placed at the vertices of this triangle, and we are having one dipole having dipole momentum P vector, and here we need to calculate the potential energy, electrostatic potential energy of the system. Okay, so let us make the diagram to the next page. Here we can take three charged particle and one dipole as a system, and in system we are having the four element. Let us number these elements. This is 1, 2, 3, and let us number this dipole as number 4. We are having the four elements. That means number of the pairs should be 6, and we can write potential energy of these 6 pair as U12, U23, U31, U14, U24 and U34. Okay, U12 is the potential energy associated with these two charged particles separated at a distance 2a. U23 is the potential energy associated with again two charged particles, and U13 is potential energy associated with the charged particle number 1 and 3. Okay, you can observe here 1, 3 and 2, 3. The separation between the charged particle should be same because this angle is 45 degree. That means this side, if it is A, this should also be A, and this should be equal to root 2a. Similarly, this should be equal to root 2a. We can write the potential energy of 1 and 2 directly by using the formula 1 upon 4 pi epsilon naught q multiplied by q divided by 2a. Q multiplied by q equal to q square. So this is the potential energy U12. Similarly, the potential energy of U13 and U23 will be equal. So let us calculate the potential energy U12 and U23. So first we calculate the potential energy U13. U13 is equal to, as we calculated, this distance is root 2a. So this value is 1 upon 4 pi epsilon naught q square divided by root 2a. So these are the potential energy U12, U23 and U13. Okay. So let us write potential energy term to the next page. Now come to this factor U14. U14 is the potential energy associated with this charged particle and dipole. So here we can write potential energy for this system equal to minus P dot E1. E1 is the electric field because of charged particle 1 at the center of dipole. For this U24 we can write minus P dot U2, right? And similarly for U34, that means dipole and charged particle, we can write the same formula, that is minus P dot E3. So this is the expression for the potential energy. Let us calculate this value P dot E1. P is the dipole moment and E1 is the electric field generated by this charged particle at the center of this dipole. We know this is the positive charge. Electric field here should be in the rightward direction like this. So this is E1 vector. We can observe the angle between the dipole moment and E1 vector is 90 degree. That means this dipole moment and energy should be 0. Similarly, we can say the potential energy associated with this pair 2 and 4 will be 0 because electric field because of 2 will be in the leftward direction. Again, angle between the dipole moment and electric field vector will be 90 degree. That means this dot product should also be 0. Now let us calculate this term. P is the dipole moment, this one, and E3 is the electric field associated with this charged particle. This charged particle is positive. That means electric field vector E3 will be in the downward direction. That means the angle between the dipole moment vector and electric field vector is 180 degree. That is pi radian. So here we can write U34 equal to minus P dot E3, this one, and this is equal to P multiplied by 1 upon 4 pi epsilon naught Q divided by this distance is again A. So this is the expression, and we know this is equal to minus 1 and minus multiplication will be positive. So potential energy associated with this expression should be equal to 1 upon 4 pi epsilon naught PQ divided by A square. So we got the potential energy U34. Now we can substitute the value. Okay. So this is the final expression for the potential energy. We can rearrange this term like this. So this is the final expression for the potential energy of the system. Now let us move to next illustration. In this illustration, we are having 3 identical dipoles and dipoles with charge q and minus q. This is q and minus q separated by a distance small a. That means magnitude of dipole moment of each dipole is q multiplied by a, and they are placed at the corner of an equilateral triangle of side D. We need to find the interaction energy of the system, and it is also given A, that is the separation between the charges in dipole, is much smaller than small d. Small d is the separation between the dipoles. Okay, so let us make the diagram to the next page. This is the situation. If we observe, all 3 dipoles are placed symmetrically. That means this pair, that is a BC pair of 2 dipole, are identical as CA pair, because if we make this line in the forward direction, we can observe here the angle between the dipole moment and the electric field of this dipole at this position should be in this direction. That means this angle between dipole moment and electric field is 120 degree. And similarly, if we prolong this line, the electric field vector because of this dipole will be in this direction. Okay, and dipole moment is this direction. That means this angle is again 120 degree. And similarly, if we observe electric field at the center of this dipole will be in this direction, that is the E vector, and dipole moment vector is in the rightful direction. This angle is again 120 degree. That means if we select 3 dipoles as a system, and if we calculate potential energy associated with any of the pair, that means multiplication factor 3 will give the potential energy of the system. That means we need to calculate the potential energy associated with any of 2 pairs. So let us write the potential energy expression for this system, that is equal to UAB plus UBC plus UCA, right? You know these 3 pairs are UBC, UAC and UAB magnitude wise same. Okay, so let us calculate any one pair. So let us select this B and C pair. Okay, so here we can write potential energy associated with this C dipole placed at position C because of the electric field of B as minus P dot EB. Okay, this is the potential energy associated with this B and C system, dipole placed and at B and C. Okay, so let us make the electric field vector. You can observe the center of this dipole at the axial position of the dipole placed at B. So electric field will be parallel to dipole moment like this. So let us write this electric field vector as EB. This is EB vector, and we know dipole moment vector is along this line. This is the P vector, and this angle is 120 degree. Now we can write this dot product as P multiplication electric field because of this dipole, and we know the electric field vector EB is equal to 1 upon 4 pi epsilon naught 2p divided by d cube. So this is minus p multiplied by this magnitude multiplication cos 120 degree. Okay, and 120 degree equal to minus 1 by 2, minus and minus will be positive, and 1 by 2 and 2 will cancel out, and it will give this value, that is equal to 1 upon 4 pi epsilon naught p square divided by d cube. Okay, this is UBC. As we discussed, UBC, UAC and UAB all are identical. That means the total potential energy equal to 3 multiplied by this value. So this is the total potential energy. We can further simplify. This is equal to 3 by 4 epsilon naught p square divided by d cube, and p is equal to q multiplied by a. So p square equal to q square a square. So this is the potential energy of the system.
Dear aspirants, Cengage India has launched the new edition of our JEE Advanced Physics books. Please visit www.cengage.co.in to buy a copy. You can also buy the books from Amazon or Flipkart.